Okay, great. So 11 people, that's about, I guess I'm not surprised by that. So this is the exam period. So some of you are preparing for exams, which is fine. This lecture will be a light lecture in a sense. You'll see it's the set identities is going to be, it's going to seem like a lot of review of the logic stuff that we took already, and then I'll introduce graph theory, and that should probably be a little bit shorter tonight, but I'm not sure exactly how long. But it'll just be an introduction to graph theory, and the other part will be mostly a review. So the first thing we should talk about is our new schedule. Can everybody hear me okay? Hope I'm not talking to myself. Yeah, all right, perfect. Okay, so here is the new schedule, and I am recording, so that's, I believe, yeah. Wait a minute. Sorry, just give me 1 second here to fix my pen. Okay. So we are here. Leave any changes to the test, not the content, no. Just the date. The content will be exactly the same. And it's unfortunate sort of the way the exams fell, that they basically took 2 of our classes, because classes don't officially resume till the 2nd. So it was suggested that any quiz we had waited until then. But I also I always want to offer the quizzes, or at least you have the option of writing them on the Monday, because that's the time that you signed up for. So that's why the quiz will be moved to here, week 9. So it'll be Monday through Wednesday. So these 3 days. And the same as quiz 1, you'll have the 3 days, and then you can start at any time, but once you start it, then you have, in this case, 75 minutes to finish instead of 60, because I want to give you time if you want to upload your answers to be able to do that. But yeah, the material is exactly the same, and nothing's really changed in the course, so we just had to shuffle some things around. So the tutorial will be pushed back to week 10, and then it sort of gets a little bit busy in there, in that we have the quiz and then an assignment and then another quiz, but it should be fine. I don't think it's, the quizzes are not big. They're all smallish, so I think you guys will be okay. And that gives you time to do your, yeah, that'll give you the week and a half coming up for your exam period. And this class will be, something you should be able to absorb sometime, and then it's not, it won't be long and it won't be heavy. So I think that's all the things I had to cover here. It does mean that tutorial 6 gets pushed back. We were going to take this week off, but you'll have tutorial 6 during that week. It says week 12, it should be 13. All right, any questions on our schedule? Okay. I think I did post it. If not, yeah, I think I posted I posted an updated schedule, and then I reposted this one. So it should be up on See You Learn. I can, okay. Yeah, I believe it's up on See You Learn, and I should throw it up on Discord too. Let me write a reminder. I thought it would go out with the email when I did the announcement, but apparently it doesn't do that. So yeah, so it's attached to on the announcement forums as well, but yeah, I'll put it basically everywhere so everyone can see it. And it still is tentative, right? Some of these things are subject to change. They probably won't, but if we run into more problems like we did now, who knows? I don't know. The world's gone crazy, so. Okay. Any other questions? All right, so let's get started with set identities and operations. All right, so let me turn off my video. Okay, and of course, my usual disclaimer: these are slides by Dr. Robert Collier, and you know, I've edited them and made some changes, so any mistakes you find are almost certainly mine. All right, so last class we talked about sequences, series, and sums. So we talked about geometric and arithmetic series, closed forms of these series, so you know, which is basically a simpler form that we can actually evaluate much more easily. Yeah, these are closed forms for sums. We talked about sigma notation, so that's a way to express a series concisely, and we talked about manipulating sums using sigma notation, all the different things you could do. And then we got an introduction to set theory, so we talked a little bit about set notation and subsets and a little bit about set operators. So we talked about the union and the intersection operators. So that was last class, and so this class we're going to continue with sets. So we're going to talk about set operations and identities, and in particular we're going to look at how to tell that two set expressions are equivalent. So we have seen some set operators, we've seen the union, we've seen set difference, and we've seen the intersection. So you can build set expressions, and we're going to see how we can show that two set expressions are equivalent. In particular, we're going to see membership tables. This is going to look a lot like our truth tables. And we're going to see how to show that set expressions are equivalent using Venn diagrams. And we're also going to look at set equivalences. And these are going to look a lot like our logic equivalences. So this might seem like a lot of review, which makes it perfect for this week, actually. And then we're going to look at graphs and graph representation. So this is basically, we're just going to introduce the topic. We're going to look at sort of the notation and the different types of things. So graph types and uses. We're going to look at how we represent them in computers. And we're going to look at some common types of graphs. And that will lead into our next lesson, which will cover more complicated things about graphs. Okay. All right, so let's go back to our sets. So this came up last week about what a subset is and what a proper subset is. So somebody asked about this type of notation here. So that is a proper subset. So A is a proper subset of B if A is a subset of B and A is not equal to B. So that means there's some, you know, if B is equal to 1, 2, 3, 4, then A might be 1, 2, 3. And then we could claim that A is a proper subset of B. That would be true. Yeah, and this definition is important because, well, for this main difference is that we want to sort of specify that A is not going to be equal to B. So it'll definitely be some subset. All right. The power set of a set A is the set that contains all possible subsets of A. And when we say all possible, we don't just mean the proper ones, so we also mean A itself. All right, so for instance, if A is equal to 1, 2, 3, then the power set of A using this notation is, we start with the empty set, because the empty set is always a part of any set. And then we look at every possible subset we can. So we have 1, 2, 3, and then we combine. So this is all the subsets with 1 element. This is all the subsets with 2 elements. And this is all the subsets with 3 elements. So if the cardinality of A is n, what is the cardinality of the power set of A? All right, so let's, what do we think? Any guesses? I mean, we can see here, we can count them. So how many elements are in this set, and how does that relate to the number of elements in this set? Does anybody have a guess? Okay, so one way we can think of it is, let's see, we got, yeah, 2 to the n. It is 2 to the n. And one way to think about it is, and maybe this will make sense to you at this point and maybe not, but if we think about binary numbers, so if we have 0, 1, 0 is a sort of a binary number. And if we have a 3-digit binary number, then a 1 represents, in this case, if we have a set 1, 2, 3, then a 1 in the second position means the set contains 2. And the zeros mean that it does not contain 1 and 3. And the fact, so a 3-digit binary number actually, the number of values that you can represent is 2 to the power 3. So this is the number of 3-digit binary values. Can there be fewer elements? So duplicate subsets. So when we're talking about sets, right, so we don't count duplicates. So no, it's always going to be 2 to the n, simply because of the way we define sets. Yeah, somebody asked if there can be fewer elements than 2 to the power n in your power set if they're duplicates. But since we don't count duplicates, it's always going to be precisely, yeah, A is not a set. So we, yes, exactly. So the example that was brought up is if A is equal to 1, 1, 3, then this is technically a multi-set. This is not a set. If we represented this as a set, it would be just simply 1, 3. So yeah, so because sets don't count duplicates, the power set always has that number. Right, so if the cardinality of A is equal to n, then the cardinality of the power set is 2 to the n. And that's simply because that's the number of ways I can take or leave every single element in that set. And you don't have to, if this doesn't make sense to you, that's okay. All right. So last time we talked about the membership operator. So this is if we want to take a specific element and say that X is an element of the set A, then this has a true or false value. Right. So yeah, this is just sort of a repeat of the definition of set membership. So now that means we can do something similar with set membership that we did with truth tables. Since these are all propositions, we can express set membership in a way that's very similar. So an element can either be in the set or not in the set. So if we have a set A here, then we can use 1 to denote the membership or presence of a particular item, and 0 is used to denote the absence. So we can have 1, 0. This is the set membership tables for the set A. So now what we're doing is we're taking sort of an arbitrary element that can either be in the set or not in the set. We don't know anything about this element. We don't even know that it exists, but we're saying if it does exist, then we put a 1 here. And if it doesn't, we put a 0. All right, and so this tells us nothing at this point, but the power is when we combine it with other sets and make expressions. So again, similar to truth tables, if we add a second set B, with truth tables, it was if we add a second proposition, we have to sort of double the number of rows. In this case, if we add a second set, then to consider all combinations, we double the number of rows. So if we have an element that's both in A and B, so this is the same element, it happens to be in set A and in set B, then we put a 1 for those. If we have an element that's in A but not in B, then we just simply put the 1 here and the 0 for B. And this is an element in B but not in A, and this is of course an element that's neither in A or B. So we're not saying anything specific about what's in the sets. We're just saying if there is, if there was an element that's in both A and B, we would express it like this. Okay, so does this make sense? Is there any questions or? All right. So again, our goal is to, do more complicated expressions. So now we want to complete the following membership tables. So what we want to do is we want to take a complicated expression and have a way to represent it, similar as what we did with logic expressions. So the final row of our truth table sort of represents our expression, and set membership works the same way. So A union B, if I have a 1 in A and a 1 in B, what should I put in this top row for A union B here? Hopefully it's clear what we're doing. Yeah, 1. All right, good. A union B, so it's, an element is in A but not in B, so what am I going to put in the second row here? Yeah, exactly, 1 again. And the third row, it's in B but not in A, so we'll put a 1 again. And then in the last one, it's neither in A or B, so let's put a 0. Perfect. All right, so what about A intersect B? So in the first row, what should I put, a 1 or a 0? Yeah, a 1. So that one should be pretty easy. What about the second row? So we have something in A but not in B. Yeah. So that's going to be a 0. The third row is, of course, a 0 as well. And yeah, and it's zeros from here on out. Good. So yeah, this should look very familiar. This might look a lot like the OR operator, and this looks a lot like the AND operator. And we saw last week using set builder notation, of course, the OR happens to factor in the set builder notation for this, and the AND in here, so maybe it's not all that surprising. What about set difference here? What about our first rule for set difference? What should we write? 0. Yeah, excellent. So it's an element that's in A, but it's also in B, so that means we're going to subtract it, and we'll get a 0. What about the second row? What should that be? 1. Yeah, excellent. All right. You guys seem to. 1. The third row? 0. Yeah, correct. And the fourth row, that's 0. And of course, the negation is simply I put a 0 if I have a 1, and I put a 1 if I have a 0. So yeah, these probably look familiar. Again, this looks a lot like the OR. This looks a lot like the AND, and this actually looks like a lot like the implication, but negated, right? So that might be, or I guess that would be A implies B might be more correct. So they are not those things, but they behave the same way. Okay. Yes, and it looks a lot like truth tables. All right, so let's complete the following truth tables. Now we're going to build more complicated expressions. And again, this is very similar to what we took, so I'm going to run through it maybe a little bit quickly since you guys seem to have the hang of it. 0 minus 1 is 0, right. All right, let's go back to that. So what we're saying here is if, so somebody asked for this line here, this row, so I have there's nothing in A and something in B, and I subtract A from B. So let's say I have well, let's say A is the empty set, and B contains 1. Since, well, yeah, sure, let's go with that. So now I subtract B from A. I'm still going to have nothing, right? If you recall the set difference, if I have 1, 2 here, and I have B equals 3, 4, then A set difference B is equal to actually still A. So these ones get ignored. So this is the case where I have something in B, but I don't have it in A. So that's this 3 and this 4 here. So if they're in B but not in A, then they're not in the final set. So that's why. It's because this 3 and this 4 are not in this A set difference B. So that means, right? So hopefully that makes a little bit of sense. Are you still lost, or are you? Right. Okay. It's something we can talk about during office hours or something if you like. So A minus B, A if B is not in A. A if B. Sorry, I'm not sure what I'm not sure exactly what your expression means. If B is not in, so B, if B is a set, then it's an element. Yeah, it's an element that's in B. So what we're asking basically, if I have an element that's in B but it's not in A, then this A set difference B, is this element going to be in the final set? And the answer in this case is no. Okay, so we're sort of answering that question. I have an element that's, I'm saying A set difference B, and there's an element that's in B, but it's not in A. So that element will not be in our final set. Hopefully that, and like I said, we can, that's something we can discuss over office hours as well if it's still a little unclear, and I could probably come up with a better example. Okay, so let's go through this then. And this should be fairly straightforward and almost a little bit of review. So B intersects C, so we're dealing with these two columns. So we have a 1 here and a 0 anytime I don't have a 1 in both of them. Right? So I have an element that's in the first row, I have an element that's in B and it's in C, so it's in the final B intersect C. And then I can take the union of the column A and the column B intersect C. So now if there's an element that's in either of these sets, then it's going to be in the final set. So I have a 1 here, 1 here, a 1 here, and a 1 here. And then in this row, I have 1 in B intersect C, so that's going to end up in the final set. And then for the last 3 rows, I have zeros. So that's our final column of our truth table. And this sort of encapsulates the behavior of this expression. So this is a full, in a sense, a full representation. All right, so how would we draw the corresponding Venn diagram? So A union B intersect C. So we can draw it as, well, yeah, we take everything that's in A, and we take the intersection of B and C, and then we take the union of those two things, so we have this entire area here. Right? So that's how we can express that using a Venn diagram. And that's, in a sense, although Venn diagrams don't have as much power as, wait, let me think about that. Well, in this case, for set membership, they are as expressive, I suppose. They do have the same power. They don't have the same power because they can't represent subsets, but we're not interested in subsets here. We're just interested in set membership. So yeah, these are equivalent in terms of their ability to express something. So how would we prove that the sets A set difference C intersect B set difference C is equivalent to this A intersect B and intersect not C, or the complement of C, C complement. That's, so I throw around, I might say negation or not, but it's technically this means the complement. But yeah, I'm very sort of informal about that sometimes. So again, so I take everything that's in A, So if I want to start with this part here, and I subtract what's in C. So that means I want to take away this part here. So I would be left with this. And then for this expression, B set difference C, I would do the same thing. So I would end up taking everything in B and then subtracting the stuff that's in C right here. So now I have this final area, and I take the intersection of those two things. So I'm going to end up with simply this area here. So now on to the other Venn diagram. I want to take A intersect B. Well, of course, that's all of this. And then I want to take the intersection of the complement of C. So that's the intersection of everything that's outside of C. So this part here is inside of C. So I want to only take that part. Okay, so then in both cases, they should look something like this. So here we have our A minus C. Here we have our B minus C. There we have our intersection. Here we have our A intersect B. Here we have our C complement, although technically it does include all the stuff that's outside of them as well. And then the intersection of C complement and A intersect B is that. Okay. Any questions on how we can show these expressions using Venn diagrams? All right, good. All right, so now we can prove that these two sets are equivalent using membership tables. So that's, again, same as the logic tables. All we have to do is show that the columns are the same. So anywhere there's a 1 in one, I have a 1 in the other. So we can fill this in really quickly. A minus C is 0 here. So something is in A and it's in C, so it gets subtracted. Something is in A but not in C, so it stays in our final set. Here is 0, here is 1, 0, 0, 0, 0. B minus C, we have 0 here, 1 here, 0, 0, 0, 1, 0, 0. And now we want to take the intersection of those two things. So we have a 1 if there's both 1s and a 0 otherwise. And then I think I just filled in the rest, yeah. So here we could take A intersect B. Well, let's run through it really quickly. So it's a 1 here and a 1 here. I'm doing these two columns. 0, 0, 0, 0, 0, 0. C complement, I simply take this column and I take the opposite. And then I take the intersection of these two columns. So I have 0, 1, 0, 0, 0, 0, 0, 0. And yeah, so here is the final column for this expression. And here is the final column for this expression. And both of them only have a 1 in one location, and it's the same location. So we can show that these are equivalent set expressions. Okay. Questions on that? Okay. All right. So similar to logical equivalences, there are equivalent set expressions that are called set identities. So again, this is should not be unfamiliar. So U being the universe. So if I have A intersect the universe, what's my set? A. Yeah, correct. So A intersect the universe is simply A. Right. If I have A union the empty set, what do I have there? So A union the empty set is simply going to be A again. Yeah, exactly. So it's just A union nothing. So yeah, A. So now the idempotent, so A intersecting itself, or A union itself. What should I get? Yeah. So all the answers are pretty much the same here. So a set that intersects itself is simply the set, and same with the union. And then sort of the opposite side of domination, we have the opposite side of identity, we have this domination. So if we have A union the universe, what are we left with? What's the set? Yeah, it's the universe again. And if we have A intersecting the empty set, then yeah, so in this case, we would universe, and we would be left with the empty set. Yeah, null or empty, yes. So A intersection with nothing is nothing, A union with everything is everything. Now again, so this intersection and union, they are both commutative, which means that A union B is equal to B union A, and A intersect B is equal to B intersect A. They're associative, which means that if I have A intersect B intersect C, it doesn't really matter if I do A intersect B first or B intersect C first. And the same thing applies to union. So if I have A union B union C, then it doesn't matter if I do A union B first or B union C. I'll end up with the same, they're equivalent. So this is the distributive law. Again, this is the same as the distributive from the logical expressions. So I take A and I distribute it over B and C, and I get A union B. I shouldn't put that up as complement. So I have A union B intersect A union C. And if I have A intersect B union C, then again, I can distribute the A over the B and the C. So I get A intersect B union A intersect C. And it's the same, in math, if we had 2 times 3 plus 4, we can distribute the 2 over the 3 and the 4, and we get 6 plus 8. So that's sort of what's happening there. So the complement rule. So A intersect A complement. So A intersect A complement. What should I be left with? So A complement. So I'm taking, so what do A and A complement, what elements do they have in common? Let's say. Yeah, it's empty. So they have nothing in common, so that's going to be the empty set. What about A union A complement? What's that going to give us? Yeah, that's going to give us the entire universe. So I'm going to take everything that's in A and everything that's not in A. Well, that's simply everything. Absorption. Yeah. Absorption means if I have A intersection A union B, well, I'm taking everything that's in A union B, and I'm taking it then I'm taking the intersection of all the things that are in A. So of course, what am I left with? A, yeah. And the same here, I'm taking the intersection of A and B. So everything that's in this A intersection B is also in A, and then I'm taking the union of that with A. So what am I left with in that case? A again, yeah. and complementation. So if I take everything that's the complement of A is simply A. So then I'm taking everything that's not in A, so to speak. Difference equivalence. So anybody want to take a guess at what this one's equal to? So this is a little more complicated. It's not quite as simple as the rest of them, but A and not B, yeah. Oops. So this is yeah. A intersect. So you said and, but it's, yeah, it's close enough. A intersect not B. So it's very similar to our implication equivalence. Like I said, this is similar to a negated implication in terms of if we want to map the set membership ones to the true in the logical truth tables, then that's what that is. So the fact that there's a difference equivalence should come as no surprise because it sort of mirrors the implication equivalence. And then of course, De Morgan's law. So if I have the complement of A intersect B, it's the same as if I switch the sign and take the complement of both of those. And here, it's the same thing. Okay, good. Question so far? All right, so now we want to prove that these two sets are equivalent using the set identities. So we want to show that A set difference C intersect B set difference C is equivalent to this A intersect B intersect not C. So we'll just run through this. It should be sort of familiar to you, just substituting the logical values in. But so right away, we want to get rid of these set differences. The same as with when we use our logic expressions, you want to get rid of the implications because the implications are a little bit harder to work with. So we can take the difference equivalence here on the left-hand side and then again on the right-hand side. So we have now A intersect complement of C and B intersect complement of C. So now what should we do now? So we want to end up here. Does anybody see a path to get there? Distributivity, so we can't do that here because the distributive only works if the sign that's in the brackets is not the same as the sign that's outside. So since these signs are all the same, you can't use distributivity. You can use what's called associativity, so we can take away these brackets and rearrange them. And we can use commutativity to reorder them. So let's see how. So we're going to go through it in sort of the painstaking detail. So associativity means that we can move the brackets anywhere we like. Commutativity means that we can move this C over here and move this B over here, or C complement, I should say. And then associativity means that we get to evaluate this first because this intersection, these are both intersections. So the order that we evaluate them doesn't matter. All right, so commutativity, that's, in this case, we're simply making this, we've moved this over to the right because we want it to look like the thing that we're looking for. And then we can do our associativity, and now what's the final step here? So all this is sort of just, that's stuff we don't really need you to do in great detail, but we're showing it in great detail here. As long as all of these signs are the same, you can apply these associative and commutative rules. What do we want to do here to get to this final, to finally get to this? Does anybody remember what that's called? I don't think I remember what it's called. Yeah, I usually have to look them up too. Idempotence, there you go. Okay, so C complement intersection C complement is equal to C complement. So now we have, we've shown that these are equivalent set expressions by using these set equivalence rules. Okay, and I believe that's it for the sets. Yeah. So any questions on these sets, the set expressions, set equivalences? All right, good. Let's see if I can exit out of here. Okay, so now I'm going to, we'll move on. I don't think we need to take a break tonight. We'll see. It depends how long this next one goes. I need to see. So we'll go on to graphs and graph representations. And we want, all right. So this will be an introduction to graphs and graph representations. We're not going to get into too many, so there are graph algorithms that we'll get into later. We probably won't get into those tonight. I just want to keep it nice and light so that you guys can focus on your exams, those of you who have exams. But it's still nice to cover a little bit of this material. Again, these are based on slides by Dr. Robert Collier, and so I've been modifying them, and any mistakes you find are almost certainly mine. All right, so introduction to graphs. So this would be considered a graph. So what is a graph exactly? Well, it's a collection of vertices, which are entities of interest. So in this case, these are locations. So we have Ottawa, Toronto, Letterkenny, and Calgary. Those are thought of as our vertices, and they're generally represented using circles, or you can use other shapes, but and they are connected by a collection of edges that represent relationships or connections between these entities of interest. So these edges are, of course, these arrows that we see here, here and here, here and here. And so you see there's a lot of information in this graph. There's a bunch of numbers. We're not sure what they mean yet. But a graph is basically an abstract representation, i.e. a model stripped of unnecessary data. So in this case, our graph could represent perhaps these 4 cities, and then flights between these cities are represented by the arrows. So an arrow from Toronto to Ottawa. So the arrow that goes right here represents a flight from Toronto to Ottawa. And then we can assign some value to it that might be the distance, the time, the cost, et cetera, et cetera. So graphs are, again, they're just a model. In math, we like models because, well, because they're simpler than real life, but they also allow us to predict things, which is why they're valuable. Okay. So any questions on this graph representation? So this is called a graph embedding, which means basically a drawing. But any questions? All right. So what do we use graphs to represent? Well, all kinds of things in computer science. So we can do flow circuits or flow diagrams. So these can be electric. They can represent traffic, water systems. So your GPS has a lot of, probably is represented with graphs underneath, although I'd have to, it's probably proprietary, but I'm guessing if I were to design a GPS or if you used open maps, then those are definitely using graphs. Social networks are a big one. So the entities of interest are the people, and then the edges represent connections. So maybe on Twitter, I might be following somebody. Or on Facebook, if there's an edge between me and somebody else, then we're friends, right? So relationships, influence. Computer networks, so the internet can be represented as a graph. So each web page could be its own vertex, and then a link can represent a connection from your web page to somebody else's web page. And bandwidth might be one of the things that we measure. financial networks, so society at large, the economy. These can be represented with graphs, and the edges can represent different transactions between different entities, corporations, or businesses, or what have you. So there's tons of different things that we can represent using graphs. Okay, so graphs are a way to represent these things mathematically, and also we happen to have a computer representation for them. So that means, generally speaking, when we represent something mathematically, we develop a bunch of operations or functions that we can run on them. So people study graphs, and then they figure out ways that we can manipulate them and use them, and then we can use all that knowledge in a computer to, to do things like run algorithms on a social network to see how influential somebody is, for instance. Okay, so we're going to represent a graph mathematically. So a graph is actually an ordered pair, a tuple. So we represent a tuple using these brackets, regular brackets, and we have V and E. So V is a set of vertices, and E is a set of edges. So the edges are they're relationships, but how they're represented depends on the type of relationship. So there's basically two main types of relationships. So we can have directed graphs. So each edge in a directed graph is a tuple with a cardinality of 2. What that means is that I use the round brackets, and I have 2 elements inside the tuple, and the order matters. So if I'm representing this edge here, this red edge, and the C is Calgary and the L is Letterkenny, then this is the tuple that would represent this edge. Order matters. And the edges are represented by arrows in this case. So when we represent them, when we represent the edges with a tuple, that means the order matters, which means these are directed edges. So we represent directed edges using arrows. Yes, good question so far. Should be pretty clear. Another thing to note, this is a weighted graph. What does that mean? That means each edge has a weight associated with it. And the weight is simply these numeric values that we assign. And you can imagine if this was distances, we could represent, say, actual locations or approximate locations. So if I put an edge with a weight of 8 in this case, then I would want, Ottawa and Toronto to be about 8 units apart. So we can have geometric graphs as well, although we're not going to get too much into that. And we're going to deal mainly with unweighted graphs. So this is simply introduction to graphs. So I'm going to tell you what all these concepts are, but we're going to mostly manipulate the simpler versions of these things. So in an unweighted graph, each edge can be thought to have a weight of 1, if you like, but it's not explicitly represented, right? So we don't have to write the 1 in. We know that each edge is simply an edge of a unit weight. Okay, so if we wanted to represent this graph, so we said a graph is a tuple, so a set of vertices and a set of edges, and so they're represented in these round brackets. So the set of vertices, I didn't realize that's spelled cold, but oh, whatever, neither here nor there. So it's a set, so we represent it with these curly braces, and then each item occurs only once. There's no duplicates, and the order doesn't matter, right? So these are sets. And then we represent all the edges. Well, there's 1, 2, 3, 4, 5, 6, 7, 8 edges. And they're all represented here with the order mattering. So this TO, so Toronto to Ottawa, is this edge here. And then this OT is this edge here. And it's a set, the edge set is a set of tuples. All right. Okay. So we can also have undirected graphs. So each undirected edge can be thought of as being two directed edges, one in each direction. Although we don't explicitly represent them in undirected graphs, what that means is basically we can go either direction on this edge, for instance. So you can think of them as two directed edges, but we don't bother representing them explicitly. In this case, again, our graph is a tuple, so it's a set of vertices and a set of edges here and here. The vertex set remains the same, but now the edge set, each edge is now a set of cardinality too. So this Calgary to Ottawa represents this edge here. Calgary to Letterkenny represents this edge here. And again, the order that we write these in doesn't matter in this case because these are undirected edges. So we could have easily have written, in this case, instead of LO, we could have written OL. And that would be exactly the same, perfectly acceptable. Good. Questions? All right. So this is a simple graph. What does a simple graph mean? Well, we have no self loops. So a self loop is an edge. In this case, it starts at O and it ends at O, Ottawa. So we can't have any edge from a vertex to itself in a simple graph. And no multi-edges. So this is, again, a simple undirected graph. So we cannot have more than one edge between, in this case, Calgary and Ottawa. So if we allow multi-edges, we have what's called a multi-graph. So we can have versions of that. It's no longer a simple graph. Most of the graphs that we're going to talk about are going to be simple graphs, not all of them, but most of them. And if it's not specified, then generally you can assume it's a simple graph. And the edge set is now a multi-set, right? So because edge sets don't allow duplicates, sets don't allow duplicates, now we have to use a multi-set. And there are different ways to represent multi-sets. We're not really going to get into them. Sometimes you represent them with square brackets. Other times you just represent them as normal sets, but you include the duplicates. We're not going to worry too much about those. We're not going to work too much with multi-sets. If we allow self-loops, we have what's called a pseudograph. So we can represent this edge, since this is undirected, as this OO. Now each edge can be represented, must be represented by a multi-set as well, since we have a duplicate element. Okay, so if we use multigraphs or pseudographs, then we have to use multi-sets to represent them. And simple graphs, you can also talk about simple directed graphs. So what that means is that only one edge means only one edge in a directed sense. So if I have a directed multigraph, I can add duplicate edges, say here. So I've added another edge going this way and another edge going this way and another edge over here that duplicates this one. And the edge set again is going to be a multi-set. And we can have a directed pseudograph. And now we have the tuple. The tuple is not a multi-tuple. The tuple is just a plain old tuple. You're allowed to have duplicates in a tuple. Okay, any questions on this stuff? Like I said, most of the graphs that we're going to see are going to be simple graphs, and they'll be either directed or undirected graphs. So you're going to see those. We're not really going to work with multi-graphs, and not so much with pseudographs. They might come up once or twice, I'm not sure. Okay, so a little bit of terminology now. Adjacent vertices are connected by an edge. So if I have an edge between Calgary and Ottawa, then I say Calgary and Ottawa are adjacent to my graph. or Toronto and Calgary are not adjacent. Okay. So we say X is adjacent to Y if and only if there exists an edge that starts at X and ends at Y. So I have X, I have Y, and I have an edge. In this case, X is adjacent to Y. Y is a neighbor of X. I say X is adjacent from Y if and only if there is an edge that starts at Y and ends at X. So adjacent to and adjacent from, those are for directed graphs. So vertices are adjacent, and they're also called neighbors if U and V, yeah. So vertices U and V are adjacent in G if U and V are endpoints of an edge in G. So if an edge E connects U and V, E is said to be incident on U, incident on V, or incident with U and V. Right. So when we talk about adjacent, we're talking about between a relationship between a vertex and another vertex. So adjacent or not adjacent describes the relationship between two vertices. If we use the word incident, we're describing a relationship between an edge and a vertex. So an edge either is incident to a vertex or is not incident to a vertex. Right, is that clear? Questions? Okay. So what type of graph, now that we've seen some of these graphs, what type of graph would be suitable for representing the internet? Or what, I mean, you don't have to specify everything, but let's say we have multi-graphs, we have pseudographs, we have directed graphs, we have undirected graphs. What's maybe one thing that we could associate with representing the internet? Right, so this is some index of Dr. Robert Collier's web page, and you can see if I'm at multi-set, yeah. Yeah, because you could have more than one link from one page to another. That's actually not uncommon. So you can have a multi-graph for certain, and also a directed graph. So everything on the internet has a direction. I click a link, it takes me from one page to another, but the link doesn't go backwards. I mean, I can hit back on my browser, but there's not always, if there's a link going one way, that does not mean that there's necessarily a link coming back. So we have to use a directed graph. So these are the types of things we want to consider when we want to model something with a graph. How are we going to model it? And then the other question, how would we represent this on a computer? So we've talked about how to represent them mathematically. We've looked at how to represent them in pictures. And pictures are quite common with graphs because they have a nice visual representation. But now, how do we represent this on a computer? Well, it turns out there's two main ways that we want to represent them. And like everything in computers, there's generally a trade-off between speed and memory. So we consider a directed graph of n vertices and m edges. We can represent that using an adjacency list. So an adjacency list is an array of lists, and each list contains all vertices adjacent from that vertex, so the neighbors of that vertex. And this, generally speaking, tends to be memory efficient, but maybe a little slow. On the size of the graphs that we look at, everything will run, of course, at lightning speed, but once you get into huge networks, these are the types of things you need to consider. An adjacency matrix is an n by n matrix of Boolean values or numbers. This is fast but bad on memory. All right. And if you don't know what matrices are, if you don't remember, we're going to see some in a minute. So here we have a directed graph. It's a, what type of graph is this? Anyone remember? Yeah, it's a pseudograph, directed pseudograph. Right, so we have, it's a very small directed pseudograph, and we're going to represent it using an adjacency list. So what we're going to do is each vertex is going to be sort of an index in an array. And then at each index in the array, we're going to store a list. Right, so I gave it away. So this is directed, so W is neighbors with itself and also neighbors with Y. All right, so then who's in the adjacency list for X then? Which vertices? Yeah, Z. So should be pretty straightforward. For Y, we have who's in the adjacency list? So that's X and Z. And then for Z, we have nobody. So this is just an empty list. So that's an adjacency list using directed graphs. This is, we can also represent them using an undirected graph. So in this case now, when we talk about the neighbors, we don't worry about, again, we can think of it as we have directed edges in both directions. So we can think of this edge as having one edge going from X to Y and one edge going from Y to X. So in this case then, who are the neighbors of W?
Found an ant in the bathroom.
Yeah. So we have W and Y. The neighbors of X then are going to be Y and Z. The neighbors of Y, W, X, and Z, and the neighbors of Z are going to be Y and Z. And what order do we write these in? We're not in particular for this class going to worry about the order. We may specify, if we tell you to do an adjacency list, we probably will specify the order. Usually it'll be in alphabetical or numerical order. That just makes it easier to mark. But when you're building these things, you can specify the order. It's not really written in stone. Z, X, Y. Oh, yeah. Right. Good catch. Okay. Now we want to represent this directed graph using an adjacency matrix. So what we're going to do here is, in a sense, on a computer, you want to do a two-dimensional array. So now we have, we look at the intersection of W and W, and if W is a neighbor of W, then we put a 1. And if it's not the neighbor, then we put a 0. So you can also use true values. True or false, 1 or 0 is pretty common. And if you use a weighted graph, then instead of a 1, you would write the weight of that edge. That's also quite common. So in this case, W is a neighbor of itself, so we'll go row by row. X is not a neighbor of W, so we'll put a 0 there. Y is a neighbor of W, so we'll put a 1. And Z is not, so we'll put a 0. Okay, and then for X, so we have one outgoing edge from X. W is not a neighbor. X is not a neighbor with itself. The edge from X to Y is going in the wrong direction, but we are a neighbor with Z. And for y, not a neighbor to w, a neighbor to x and z, but not to itself. And z is neighbors with nobody. Now, the nice thing about this representation is that you can actually multiply matrices to get, you know, neighbors that are 2 hops away. So if I'm not sure, I can't remember off the top of my head the exact operation. It could be I just multiply this by the matrix transposed, but I'd have to look it up. But you can easily compute sort of from W, I can find the neighbors that are 2 hops away, and so on and so forth. All right. And this works for undirected graphs as well. But now in this case, we don't want to think about direction, or we want to assume that both directions exist. So here we have W is not connected to X, but it's connected to itself, and it's, oops, oh, there you go. Connected to Y, not connected to Z. X is connected to Y and Z. Y is connected to W, X, not to itself, but to Z. And Z is connected to not W, X, Y, and not to itself. All right. So let's take away the self loop and now look at the adjacency matrix for a simple undirected graph. And is there anything that we noticed about this? What sort of properties might we say that this matrix has? Yes, because it's a simple matrix. It has zeros along the main diagonal. Yeah, that's a good observation. So no self loops. So that means the main diagonal must be all zeros. What else? Is there anything else that we notice? Equal to its transpose? Yes, it's symmetrical. Exactly. So if we draw a line down the diagonal, then one side is symmetrical to another. It's mirrored, in a sense, along this line. So those are 2 sort of sanity checks. If you're ever given a simple graph and you're asked to do an adjacency matrix, those are 2 easy sanity checks to make sure that you haven't made an error. Well, it doesn't mean you haven't made an error, but it does eliminate certain types of errors. Okay, good. Any questions on adjacency matrices or adjacency lists? All right. Okay, so another thing when we talk about graphs, we talk about the degree of a graph. So the degree is important. So the degree of a vertex is the number of edges that are incident on that vertex. So we talked about incident is the relationship between an edge and a vertex. And that becomes important because if you have what's called a high degree vertex, so in this case, Y has our highest degree, that's something you want to sort of avoid. If I'm building a model of something like a computer network, I don't really want to have a high degree vertex because then I have to handle all those incoming and outgoing messages, and that gets expensive. I need special switches to do that. So the degree of a vertex is rather important in when we're building our models. So the degree is the number of edges that are incident. So the degree of X is what? Yeah, the degree of X is 2. The degree of Y is 3. The degree of Z is 2. The degree of W is what? What should we put there? Is that for the, yeah, the degree of W should be 3. So pseudographs are a little tricky that way. Yeah. It looks like I did my homework on this slide. So yeah. So with a directed graph, we have in degree and out degree. So if we talk about the in-degree of each vertex, then we're talking about the number of incoming edges. So for x, that would be 1. For y, that would be 1. For z, that would be 2. And for w, that would be 1. Yes. And we also have, of course, out degree on a directed graph. So the out degree of x is 1. The out degree of y is 2. The out degree of z is 0. And the out degree of w should be 2. Okay. Any questions on in degree and out degree or degree? All right. So let's say that we have a graph. Our graph is G equals V, E. So V and E are the vertex set and the edge set. And we have our function DEG that returns the degree of a vertex in an undirected graph. So if we summed up the degree of all the vertices, what do we get? Does anybody know or want to take a guess? 2 times the number of edges. Yeah, exactly. We get 2 times the cardinality of the edge set, or 2 times the number of edges. Does this make sense? Why or why not? Well, it does happen to make sense. And it's based on what's called the handshaking theorem. And how the handshaking theorem goes is that one handshake is experienced by 2 people. And then by the same token, one edge contributes 2 to the total degree, since each edge by definition has to have 2 vertices. And we're talking undirected here. If we were talking directed, it would be the sum of course, the in degree and the out degree. Right, and so let's take a look here. So we have the degree of all these vertices. So 2 plus 3 plus 2 plus 3, that's 10. That's the total degree of our graph. And 2 times the number of edges, well, we have 1, 2, 3, 4, 5 edges. So that's also equal to 10. Okay. Any questions on degree? Pretty straightforward. Like I said, this is going to be sort of a light lesson. And I think we're almost, we have a few more things to look at, but maybe 10 or 15 minutes more. So a complete graph on n vertices is denoted by this k subscript n. The vertex set has n vertices, and the edge set is edges between all possible pairs of vertices. So every vertex is connected to every other vertex. And again, since we didn't specify, these are simple graphs, simple undirected. So K2, I would have the vertex set is 2, and I would have an edge between all pairs of vertices, so I would draw one edge like that. For K3, the vertex set would be 3 vertices, and to have an edge between all pairs, I have an edge here, an edge here, and an edge here. And that's it. So that's K3 is a triangle. Oops. Oh, K4, spoiler alert. I draw my 1, 2, 3, 4 vertices, and then I draw an edge from each vertex to every other vertex. So in this case, you'll notice that the degree of all the vertices of K2 degree is 1. The degree of all vertices in K3 is 2. And the degree of all vertices in K4 is 3. Again, these are just, these aren't deep observations or anything, but these are little sanity checks you can do. So for n vertices, how many edges in general? Well, let's take a look at it. So for vertex A, so that wasn't supposed to be here yet, but vertex A, though, we're going to connect it. So this is going to be K5. So we're going to start with vertex A and connect it to every other vertex. So that has degree 4. The 4 edges from A, 1 to every other vertex. Then we go to B. Now there's already an edge from A to B, so we have to connect B to everybody else. So now we get 3 more edges. And now we're going to look at C. Now C is already connected to A and B, so I only have to connect it. I'm left with connecting it to D and E. So that means another 2 edges there. And now D it's already connected to 3. I only need to connect it to E. So I have 1 edge coming from D. So that's going to be sort of familiar if you remember from our summations. It's going to be the sum from I equals 1 to n minus 1. So if I have 5 vertices, it's going to be the sum of all the numbers from 1 to 4. Oh yeah, and E is of course 0. All right, and so then we have a nice nifty closed form for that. And one thing to notice about this is sort of approximately n squared. It's quadratic. So storing complete graphs, although it can be in a sense, optimal in terms of the information that you stored, it's going to be very expensive in terms of memory. All right. So a cycle graph on n vertices for n greater than or equal to 3 is denoted C subscript n. So the vertex set has n vertices, and the edge set has an edge between all possible edges of the form. So if we put an order on our vertices, then we're going to draw an edge between each vertex, each pair of vertices in order, and then between the first and the last one. So it's exactly as you might expect. Well, C2. So we said for n greater than or equal to 3, but technically, we talked before about vacuous proofs. This is a cycle graph by a vacuous proof. Even though there's no cycle there. Yeah. So C3, I just take my 3 vertices and I connect them in a cycle. C4, again, if I numbered them, we don't want that, we want. So then the edge set would be 1, 2, 2, 3, 3, 4, and 4, 1. All right, so that's our edge set for C4. And then C5, again, it should be simple enough. You're going to do your best to make a wheel and then connect all your edges in a cycle. So a wheel graph on n vertices for n greater than or equal to 4 is denoted Wn, W subscript n. The vertex set has n vertices. And the wheel graph is the same as the cycle graph of 1 less vertex, but the additional vertex is connected to every other vertex. And the reason why it's called that is, well, if I take C3, and then I add a vertex, and so now we have W4. W5 would be C4, so that's the cycle graph on 4 vertices. But now I put an extra vertex and I connect them to everybody else. And I don't have to draw it like a wheel. It's actually, this is also a wheel graph. And W6 is, of course, the same thing on 5 vertices. Good. Anybody notice anything else about these? I mean, in particular, W4. Have we seen that graph before? Anybody remember what that was? It's K4, yeah, that's right. It's a complete graph on 4 vertices, so this is also the K4. And if you recall, this was K3, and it's also C3. So yeah, when we have a low number of vertices, some of these graphs are the same. Okay. Bipartite graph is a graph where we partition the vertex set into two different sets of vertices such that V1 union V2 is equal to the vertex set and V1 intersect V2 is equal to the empty set. And all that means is that if I have a bunch of vertices, I'm going to take them into two sets that have no overlapping vertices, right? So that's essentially what I'm saying with that. So, and every edge has one end in V1 and one end in V2. So if I have two sets of vertices, so up here we have V1, and down here we have V2, then bipartite means that edges only connect vertices from V1 to V2. I do not have any edges between vertices in V1, so this is not allowed. Oops, and I don't really want to make a directed edge, so this is not allowed, or between vertices in V2. So if I had either of these edges, this would not be a bipartite graph. And we can talk about a complete bipartite graph, and we represent it with K subscript Mn, and it has partitions of size M and N, and every element in V1 is connected to every element in V2. So again, here's V1 of size N, V2 of size M, and then we add every single edge possible. So every vertex in V1, because V2, the size of it is 3. So this has, each of these has degree of 3. Actually, degree of 3. And likewise down here, this set has 2 vertices, so each of these has a degree of 2. And again, we're not allowed to have edges between vertices in the same set. And we can say, do K33, and we add every edge in. This is the complete bipartite graph, K33. All right. Any questions on bipartite graphs? All right. Let's go to, that's as far as we're going to go today, but maybe we want to think about, I don't know, we'll just stop there. So it's 7 o'clock. So we did a half lecture. That should be good for this week. So you guys have time to prepare for your exams, those of you that have exams, and we still got, you know, at least something in. All right. Is there any questions? Okay, good. All right, that's it for tonight. Good luck on your exams, everyone, and I'll stick around for another 10 minutes or so to answer questions. Yeah, you guys have a nice day too. Hopefully you have air conditioning, because it is sweltering in here.